I will begin. I will begin with a word of prayer. I think it's time, so here we go. Heavenly Father, we thank you for this day. I thank you for these students. Again, I just pray that you'd guide our steps today. We thank you that while we were sinners, you first loved us. And thank you for your love and your forgiveness and your mercy to us each and every day. And just pray again that you'd be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. Let's see here. You guys all top hatted, very exciting. Let me work another problem with circles before I forget. So, example 1. So let's suppose we've got a circle.
That's really good.
And we've got one point which is like, I don't know, minus 3 comma, let's say 5. And we got another point up here which is, I don't know, 5 comma 13. All right. And in addition, you're given minus 3 comma 5 and 5 comma 13 fall on the endpoints of a diameter of a circle. All right. Here's the question. Find the equation of this circle. So this one's, I think, a little bit different than the ones I worked for you last time, right? A little bit different. So how should we do this one? What do you guys think? What is a diameter to start with? A diameter?
That's 2 of the radius.
It's 2 of the radius, right? It's a chord that goes through the center of the circle, right? And just like you said, you've got radius here, you got radius here. That's true.
Radius squared times 5.
It is, hey. That's not where the corner should be. What the what? It's not cool. Look at that. They should put like a foam noodle on this or something.
Are you a toddler?
No, but it's here. It's very pointy and hurty for your elbow.
Right.
All right, so question. Where's the center of the circle? How do you find it? What is the center of the circle?
Midpoint.
I heard midpoint. That's music to my ears. The center of circle is midpoint. Come on, marker. Midpoint of minus 3, 5. Man, I'm having trouble writing minus 3, 5 and 5, 13. How do you find the midpoint of 2 points?
Take a graph to do that.
You do not need to graph now.
I need a graph.
So a simple way to do it is if you want to find the midpoint of 2 points, like midpoint of P and Q, the simple thing to do is just take P, add it to Q, divide by 2. That's going to be the midpoint, which is, yeah, so I do minus 3, 5. So yeah, you're telling me what that means. And I appreciate that. So you're like, that means you add the x's, right? So minus 3 plus 5 is what? 2, right? And 13 plus 5 is 18. And then you can divide that by 2. What that means, of course, is 2 over 2. 18 over 2, also known as 1/9. Another student in another section said, well, what you do is you take the average of the x, take the average of the x's, and you take the average of the y's. That gives you the midpoint. That's exactly the right idea. The average of 5 and minus 3 is 1. The average of 13 and 5 is actually 9, right? That's midway between those two. on the number line. So anyway, here we go. The center is 1, 9. That's the center. What's the radius? So like last time, I used the notation x naught, y naught for the center, right? So you guys, how do I find the radius? What is it? I mean, you could either do the distance from the center to 513, or you could do the distance from the center to minus 3,5. Let's do the distance from 513 to 19. If we do that, then that's the square root of like 5 minus 1 squared, right? Plus 13 minus 9 squared, which is what? 4 squared, so the square root of 16 plus 16, right? Which is the square root of 32. All right? So what's the equation of the circle? Now we know its radius, we know its center, right? Remember last time we defined a circle as being what? X minus x naught squared plus y minus y naught squared equals to r squared. So this generic template for the equation of the circle, what is it? How does it play out in this circumstance? It plays out as x minus 1 squared plus y minus 9 squared equal to r squared. What's r squared? Yo. Nobody? 32. Yeah. And there you have it. That, my friends, is the equation of the circle that we are looking for. So the main thing with all these circle problems is, remembering what we're anchored to. We're anchored to this equation, right? This equation is the circle. So we're looking to understand how to get to or from that equation to other data that we're given. That's basically it. Either, like we looked at last class, sometimes you have to complete the square to change the equation that you're given to look like that equation. Or in this one, we have geometric data that we can use to inform us on how to set up the equation. But that's kind of just about it for us here. Yep. Glad to help. Other questions? Any other questions you guys would like to answer for yourselves? No? Okay. Just messing with you. I didn't do the half-life problem yet in here, did I?
Nope.
I did not. So let's look at example 2. So, oh, by the way, there's a... So, by the way, that's the end of circles, okay? Until you guys ask about them again, all right, on a review day or whatever. But now we're moving on to the applications of exponentials and logs. So that was section 2.2. We are now transitioning over to section 4.6. All right, section 4.6 is where we look at word problems based on exponentials and logs. So here's one. Find the half-life of radioactive element which decays according to the amount at time t is equal to the amount at time 0, which is a sub naught, times e to the minus 0.0333 t, where t is in years. So do you guys understand what this question is talking about? You ever heard about radioactivity before? Yes? How does radioactivity work? What's the deal? What's that? Did you say radio waves? That's funny. So radioactivity is a consequence of something called the weak force, right? And the weak force says that certain elements are basically unstable, and as time goes on, they randomly have these elementary particles emanate from them, and in so doing, they change the nature of the nucleus that's in question. So, for example, things like uranium. If you have uranium and you have a kilogram of it, right, and you wait a long, long time, you won't have a kilogram of uranium anymore, at least not of the same type. You'll have like a half a kilogram, right? The amount of time it takes for that to happen is called the half-life, all right? But you can apply this to things other than radioactivity, right? You could talk about like bologna in a refrigerator, right? You could talk about the half-life of bologna, you know, to a certain amount, like maybe set a certain threshold for once that piece of bologna has a certain amount of, like, you know, E. coli or whatever, pick your favorite bacteria, then you can declare it to be no longer bologna, right? Actually, how rotten does a piece of bologna have to be before it's no longer bologna? What do you think? Does it have to change color? Like, at what point do we say it's no longer bologna? What do you think? Like, at what point does a grape become a raisin?
When it's not got juice in it.
It doesn't have juice in it, but raisin's got a little bit of juice.
They have juice in it.
It's a little bit of juice in a raisin.
When it's squished and dried out. No, that would be like an apricot.
Mm. So anyway, the good news is for uranium or things like elementary particles, this is not an ambiguous question because there's actually like a fundamental change in its nature, right?
Yes.
Anyway, so a half-life is when you've got a half of the thing left, all right? Notice that the way this equation works, let's understand what the constant in the front of the equation means, right? Notice that if we plug in times 0, what do we get? A sub 0, e to the what? What's 0 times 0.3333 minus? It's just 0 again. What's e to the 0? It's 1, right? So at time 0, that coefficient in front is the initial amount, all right? So that's part of the reason for the label a sub 0, right? So how much, when you have a half-life, like how much amount is left? So for at t, so for the half-life time, let's say t is the half-life time, we have, you know, a of t equals to what? Equals to a sub 0 over 2, right? That would give us the half-life, whatever time achieves that. So we set that equal to a sub 0 e to the minus 0.0333 t. And solving this equation should tell us what time is the half-life. So can we solve that equation? See, one of the interesting things about this is it doesn't matter how much the initial amount is, right? Whether it was a kilogram or 10 kilograms or 100 kilograms, it still takes the same amount of time for a half of it to radioactive decay away, right? So, okay, so we divide the a sub naught and we're left with what? 1/2 equals e to the minus 0.0333 t. Can you guys solve that? What do you do? Anybody? It's all good. I'm just checking my mic. La la la. We're good. I guess it's still early. I'm going to take the natural log of this equation. Natural log of 1/2. Natural log of, is that what Olivia?
Yeah, she said take the natural one.
But it only counts if you speak up. So, sorry.
You gotta talk like all the people.
You know, there were like ancient Chinese and stuff who could do calculus. Like there is evidence that, you know, there are Chinese mathematicians who knew something like calculus, like, I don't know, hundreds of years before Newton and Leibniz. Why aren't they credited with it?
You're right.
Because they didn't speak up, right? Well, or it's because they had a notation which was really only accessible to those who could write Chinese, and
Oh,
even then, only those who were really
your
quite
keys
mathematical.
Look like it,
My T's kind of look like what?
like a Chinese symbol.
Oh, thank you.
Yeah, no, they're really
Oh, okay, well, I'll allow it. I also write it like this. I can't decide sometimes like this. Yeah,
Ooh, that's pretty too.
yeah, you can go that way too.
That's why I like to write mine. It's like a back, it's like a J.
Yeah, the danger with all of these is when they become too much like pluses, then it leads to confusion. Yes.
Yeah.
Oh, okay. So let's finish this thing. We've got many more of these to do today. So minus 0.0333t is what you get there, right? Because natural log and exponential are inverse functions. So then solve for t. You've got t is equal to the natural log of a half divided by minus 0.0333t. And then at this point, I need my calculator. See what we get. I get 20.815. So this tells me I should write my answer as t equals to 20.8 years. The reason,
It'll take to make that a half-life?
yeah, this is, that's, not typical. Like typical half-lives are like, well, thousands of years, yeah. Tens of thousands of years. Actually depends on the thing, There are radioactive dyes which have half-lives of days, something like that, yeah.
So we always use like 1/2.
I always use well, it depends on the question. Here, this question was about a half-life. That's why I used a half. So, like here, but this is essentially this is like number 4 in week 13 homework, right?
Is this like chemistry?
Is this like chemistry?
I never took chemistry.
You never took chemistry.
I suppose this is,
Definitely take a class.
so yes, and I don't know, like when I was in school, I took about, I don't know, 3 or 4 different classes which covered this material. I saw exponential decay in something like 4 classes personally. Yeah. No? Oh, okay. That was just a stretch? Okay, I'll allow it. Let's see here. Here, this one is not about half-life. This one's a little bit different. Number 5. I'll do my number 5 for you guys. Oh, the reason 20.8 is it said to round to the nearest tenth of a year, okay? That was why I rounded it like that. It's the instructions in the homework. Here's the question. If 12 grams of a radioactive substance are present initially, 12 grams are initially present, and after 7 years, oh man, after 7 years, only 6 grams remain. Oh man. How much of the okay, fine. How much of the I thought it was going to ask me what's the half-life, and I was going to be like, well, apparently 7 years. But anyway, so then here's the question. How much of the substance will be present after 18 years? $18. So, okay, so like there's a way to make this problem easier, right? See, half-life. So like, if you know the half-life, right? Well, here, let's go back to my example too. So, what if I wanted the quarter life? How long would it take for it to be a quarter? You just double the half-life, right? Because if you half the half, you get a quarter, right? So, if I went to 41.6 years, I would have a quarter of the initial substance, right? If I wanted to have an eighth, I would go to 3 times the half-life, right? If I wanted a 16th, I'd go to 4 times the half-life, because you'd want to cut it in half 4 times, right? A half times a half times a half times a half times a half is a 16th, right? So here, I've got 12 grams. It takes me 7 years to cut it to 6 grams. That's a half-life, right? So apparently the half-life here is 7 years. If I do 14 years, it should be cut to a quarter, right? So like 14 years would get me to what? 3 grams, right? But I'm not at 14 years, right? I'm at 18 years. Now, if I got all the way to what? To 21 years, that would be 3 half-lives for this problem, yeah? So then I would be to, 12 over 8 grams. So I know the answer is somewhere between 12 over 8 and 12 over 2, right? I mean 12 over 4. So I'm pretty sure the answer should be between 3 and, between 3 grams and 1.5 times, well, I can't do it in my head, but anyway, it's a little bit more, it should be a little bit less than 3 grams, I think. All right, so anyway, let's do the math here. Those are just qualitative comments, right? I can say all of that without writing a thing, right? You can see from the numbers that the half-life here, it goes from 12 to 6, that's half, right? It takes 7 years, so that means the half-life is 7 years. Okay. So anyway, here we go. What we know is that A of t is equal to A0 e to the minus, let's say, kt. So k is the decay rate. A naught is the initial amount of, we know what A naught is though, right? So I can put that in. We know that in fact A of t is what? A is equal to 12 e to the minus kt, right? But can we figure out what k is? What else do we know? So this 12 told me to put that 12 here, right? And I'm using what I learned in example 2, right? Which is that the number multiplying in the front is the initial amount present for the formula, right? Then what? Well, I know that if I look at 7 years, A of 7, right? It's equal to 6, and it's also equal to 12 e to the minus 7k, right? So I can solve that equation and figure out what the decay rate is. Solve for k. What do we get? We get 1/2 equals to e to the minus 7k. We take the natural log of both sides. We get natural log of 1/2 equals to the natural log of e to the minus 7k, which gives me minus 7k, which then I can solve for k. I get k equals to natural log of 1/2 over minus 7. So what's my k equal to? Now you could leave that symbolic if you wanted, right? You could do that, but I'm going to find a decimal just to make things a little bit friendlier. So, and I'm going to keep about 5 digits just to be safe. Minus 0.09902. That should be enough for us and our purposes here. So there's your decay rate, minus 0.009. There's not minus there because minus and minus give me a plus, but is that it?
No, I have a question.
Go for it.
Up there where they go 7 equals 6 equals 12e to the negative 7k.
Mm-hmm.
Where did the 12 go in the next one?
Where did the 12 go in the exponent? Oh, I just divide both sides of the equation by 12. Yeah.
I didn't, okay.
We're 6 divided by 12. Oh, that's what 1/2.
Uh-huh. Sorry, wasn't trying to be tricky. Okay, great. So now we know what k is. Okay? Oh, sorry. That was unintentional. But it was bound to happen. So what we got is, to reiterate, I have now shown you that A of t is equal to 12 e to the minus 0.09902 t, where t is in years, yeah? So now how do I answer the question? See, now I can answer the question, right? How much of the substance present after 18 years? That would be A of 18, yeah? And so that is going to be 12 times e to the minus 0.09902 times 18.
I thought the negative was there.
Well, it did, but it came back because I wrote minus KT here. Yeah.
K is half.
K is the decay rate. Yeah, usually K is called the decay rate. And here it's in years. All right, so I need to work that out, yeah? So here we go. E to the minus 0.09902 times 18 is what it is. That multiply that by 12, and I get 2.0189, let's say. And that's in grams. Now the instructions for the problem say 3 decimal places, round to 3 decimal places. So the answer would be 2.019 grams. For me, at least. Any questions? So this kind of problem, what you want to do is remember that the guiding equation, the radioactive decay equation, was given back in example 2. Namely, A of t is A naught e to the minus decay rate times time, right? And then if you're given various information, you can plug it into the equation. Then you use, how we know to solve for logarithms and exponentials to find your way to the answer. That's kind of all there is to it. All right, let's work another one here. Let's see here. So the next problem was about an Egyptian mummy and some stuff, and I'm going to skip over that one because I believe the Egyptian mummy problem is really the same mathematics as examples 2 and 3. All right. So it's about that carbon-14 dating thing. Yeah. I mean, so the math is not wrong. It's just I think the assumptions of the method which are wrong, So, but anyway, if you want to read about that, of course, you can look at, for example, like answers in Genesis and things like that. There has,
Meaning like the timing is off?
yeah, in terms of how it can be corrected and things like that. It's really only reliable in as much as it can be anchored to a historical record, which we don't really have reliable historical records from before about 3000 BC or so. I mean, you can go to national parks and they'll tell you about various this and that from 20,000 years ago, but when you actually look at what they're basing it on, there's like a tooth. So I don't know. It was very striking to me. I went out west and we went to one of these, I think it was petrified forest, which is very cool, but very boring also. I mean, the rocks don't move, but they're cool. But it's funny, like they have various, here's the archaeological evidence for this civilization 500 years ago or 1,000 years ago or 2,000 years ago. It's like, oh, okay, kind of makes sense what you're saying. And then all of a sudden, and then there was these other things 15,000 years ago, blah, blah, blah. And it's like, how do you know that? Oh, there's a tooth. It's like, so you saw all that from a tooth. It's like, I don't know. I just don't buy it. Whatever. Okay, so where was I? Example 4. So anyway, all of that to tell you that your math homework is not an endorsement of carbon dating, okay? So anyway, it's just an interesting problem there. I do think it's important for us to understand these equations so that we can meaningfully interact with them, right? And okay, so here we go. This is Newton's law of cooling. Newton's law of cooling, number 7 in your homework. And sorry, I'm trying to read the. So he I don't usually use. This is funny. He uses f of t for the temperature at time t, which is weird. The previous homework, the last problem in like week 12, used a big T for the temperature in this formula. So the book is not being consistent with its, yeah, it's lettering, exactly. Anyway, this is Newton's law of cooling. Here, this is the temperature at time t. And what are we told? We're given, you got a cup of coffee. Its temperature is 140 degrees Fahrenheit. It's placed in a freezer with temperature 0, all right? So you got a cup of coffee, 140 degrees Fahrenheit. You put it in a freezer. It's a very good freezer, yes?
It's a very good freezer.
Okay, so and the freezer is,
2D, like 3D.
oh,
Yeah.
okay, there's 3D now. 0 degrees, I'm sorry, I didn't bring you guys glasses or anything. 0 degrees Fahrenheit. And then we're told after 10 minutes, the temperature of the coffee, so this is T equal to 0. Then after, well, let's just say this. At T equals to 10, we have the temperature of the coffee is equal to 62 degrees Fahrenheit. All right. And then the question is, use Newton's law of cooling to find the coffee's temperature after 15 minutes. All right, so find the temperature at 15 minutes. All right. So the temperature at 15 minutes would be F of 15, right? The trouble here, of course, is that you don't know at the start what is T sub 0, what is C. So let me explain that to you. So here, for this problem, T sub 0, so I'm going to write my solution in red, okay? The T sub 0 is the ambient temperature. So in the freezer, the ambient temperature is 0 degrees, right? And C we don't know, all right? But what we do know is that that F of times 0 is what? It's 140, right? And so that's also equal to what? It's equal to plugging in 0 into the formula. So, which is T0 plus C times e to the 0, right? Which, by the way, T0 was 0. So this is 0. And this is just equal to C times 1, which is C. So apparently, C equals to 140. So what we find then is that T of time t, oh man, F of t, which is why he's using F rather than big T to avoid that, I guess. Anyway, so it is 140 e to the minus, e to the minus kt. Well, okay, so we still don't quite have the formula down, do we? Because we still don't know the decay rate, right? That K describes how fast the temperature, the heat in the coffee is lost to the freezer, basically, right? So it would be different if you had like an insulated mug versus an uninsulated mug, blah, 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 stuff like that, right? So how do we find K? What else have I not used? Oh, there's another piece of information we haven't used yet, right? At T equals 10, we have F of 10 is 62. So I have to use that to figure out what K is. So here we go. F of 10, which is 140 e to the minus 10k. What's that equal to? It's equal to 62. I can solve for K now, right? Okay, so what's K? So I divide by 140. I've got e to the minus 10k equals to 62 over 140. And if I take the natural log of this, I get minus 10k equals to the natural log of 62 over 140. Which then tells me that K is equal to the natural log of 62 over 140 divided by minus 10. So this is a lot like the last problem, except that with the Newton's law of cooling, you have three things to think about. You've got the ambient temperature, the initial temperature, and the decay rate. Whereas with the last problem we worked, you just had what? You just had like the initial amount and the decay rate to set the formula up, right? So Newton's law of cooling, it's a little bit more sophisticated in that regard. Oh, there's my calculator. It's like, where's my calculator? Here it is. So we got natural log of 62 divided by 140. And we divide by minus 10. Let me actually just divide by 10. And then I'll put a minus in. So I get k is 0.08145, let's say 1. I'll keep 5 digits there, yeah? So what's my formula? My formula then is f of t, 140, e to the minus 0.08145 times t. And then what was the question? The question was, what's the temperature of the coffee after 15 minutes? So what do I have to do there?
Put 15 in place of the T.
Yeah, plug in 15 for t, and that should be it. So f of 15, 140 times e to the minus 0.08145 times 15. So you plug that into your handy-dandy calculator, see what you get. E to the minus 15 times 0.0814151 times 140, I get 41.282. And what are the instructions to the problem? What do they tell us about rounding? They want the nearest integer. So what's that? Rounded to the nearest integer, what do we have?
41.
Yeah, 41 degrees Fahrenheit. Question, follow-up question. What if they asked you, how long does it take the coffee to get to 10 degrees Fahrenheit? How would you figure that out? How much time does it take? Obviously it takes more than what? Common sense here, right? More than what? More than 15 minutes, right? If it takes 15 minutes for the coffee to cool to 41 degrees, how long will it take it to cool to 10 degrees? It's not linear, by the way. Like, you might be tempted to think, oh, well, it took 18 minutes, right? It took 18 minutes to cool from 140 down to 41, so that's about 100 degrees in 18 minutes. So maybe about every 1.8 minutes, it cools 10 degrees, right? So if I wanted to cool to 10, I need like 3 times 1.8 would be like something like an additional 5 minutes. And I think you'd be wrong. You'd be approximately right. It's about another 5 minutes, probably be about 23 minutes. How would we find the precise time if Newton's law of cooling is right? It gets to 10 degrees Fahrenheit. What do you have to do? Yep.
Would you plug in the 10 when you plugged in the 15?
No. Well, right kind of idea, but we can't plug in the 10. 10 isn't the time. But we want it to be equal to 10, right? It said it equal to 10 is the idea. So what we do is 140, e to the minus time we don't know, 0.0, what is it, 0.08145 times the time we don't know, right? And that's equal to 10. So you solve that equation for 10. That's how you'd find the time when it gets to 10 degrees. See, because the logic of the problem is different than the one that's given here, right? But we could do that. Let's go through that. How we find t. T would be what? E to the minus 0.08145 time we don't know, 10 over 140. You take the natural log of both sides. You get minus 0.0814. I regret keeping so many digits there. T, natural log of 10 over, that's just natural log of 1/14th, right? Can I do that? Natural log of 1/14th. And so we get the time is the log of 1/14th divided by minus 0.081451, whatever that is. My guesstimate was 20 minutes, but I said I was going to be a little bit wrong. How wrong am I? Oh, I said 20 minutes. I meant 18 plus 5. It should have been like 23. I should guess like 23. Let's see what we come out to. Natural log of 1 divided by 14. divided by 0.081451. Did I? Yeah. Whoa. Yeah, it's actually kind of a lot wrong. 32.4. So I think this was all in minutes, right? So as you can see, it is not linear. In fact, it takes longer. It takes longer for it to cool that additional, 30 degrees or so.
And this was, if it was say equal to 10?
Yeah, this is how long it takes. At 32.4 minutes, it cooled to 10 degrees Fahrenheit. So to get from 41 degrees, it was at 41 degrees at 15 minutes, right? It took another 17 or so minutes for it to drop 30 more degrees, right? So think about that. In the first, let's see here, in the first 15 minutes, it drops 100 degrees, right? In the next, well, I guess that's about 15 minutes, approximately, In about the next 15 minutes, it only drops 30 degrees. It's only dropped a third of the amount, in some sense, in the second half of the story that it did in the first, which just speaks to the fact that if you have coffee that's hot, right, it loses temperature at the start much quicker than it is at the end. So what's a practical application of this observation? Should you wait to put cream into a coffee if you want to keep it hot? Or should you put the cream in at the start? You should put the cream in at the start.
Because then the cream gets hot?
No, because that whatever temperature is lost from mixing with the cold cream, right? That makes the temperature of the coffee closer to the ambient temperature of the room, which means it loses temperature at a slower rate. So it's always better to put the cream in first to keep it hotter longer. So like keeping the coffee hot and then putting the cream in later just makes the coffee lose energy faster while you haven't put the cream in, basically. If the cream is yes, if the cream is room temperature, then that destroys the whole purpose of the cream, which is to make the coffee not burn your mouth, right? But all right, so listen here, guys. I don't have enough time to do other word problems here. Let me skip ahead to do problems I do have enough time for. So there's about another 5 word problems here. I'll keep chipping away at them. I'll do like 1 or 2 a day. I don't want to do 5 in a day again. Did I do 5 a day? Maybe I did 4. I don't know.
Like 7 last time.
Yeah, but those weren't word problems. Take forever to do in class unless I have them projected. Yeah.
I know this is ahead, but like for our pages, for like the final exam, how many sheets do you get?
Well, that is a perfectly legitimate question to ask now. That is a good question to ask now. How many pages of notes are you allowed for the final exam? The answer is 3. My design there was that you could just take the 3 pages of study notes, front and back, 3 front and back pages, that you could take the 3 front and back pages you'd already prepared for the quiz and the test and just use those again, right? But if you're not content with your existing formula sheets, then make new ones, right? And by the way, if you know somebody else in here that you want to copy their formula sheet because you think their formula sheet's just the most awesome one ever, that's also fine. But you should keep in mind that you've just cheated yourself out of a valuable part of studying by doing that, because like the whole process of creating the formula sheet is the studying. It's a lot of it. What's that? Yeah, front and back, 3 sheets, each front and back. So that's actually 6 total pages of information. So you can be prepared for, well, listen here. So the next topic.
I'm going to be crying writing my notes.
So I'm going to do a little bit more on solving word problems. Not today, but the other thing we're going to be doing this week, and I want to start doing right now because we still have a couple minutes, is systems of equations, right? So what are systems of equations? I just want to talk to you a little bit about what we should expect for systems of equations. And I'm going to just tell you this much. So if you have 2 equations and 2 unknowns, what's it look like? It's something like this. You've got ax plus by equals to c, and you've got, let's say, dx plus ey equals to f. So these are two equations and two unknowns. What are the unknowns? The unknowns here are x and y, all right? What is the solution set for two equations and two unknowns? Listen, that's all I want to tell you right now in the minute we have left. We can understand this. We can expect what we're going to see here graphically. See, because each one of these equations is represented by what? By a line, right? So you could take these two equations and you can solve them for like y is equal to m1x plus b1 and y is equal to m2x plus b2 if you like. That's usually true, but those lines could be vertical lines, so what I'm saying isn't quite true. Yeah? But the fact remains that these two equations can be solved for y or whatever. They could be understood as lines, right? So if you have two lines, what are the possibilities? There are three possibilities. Three possibilities, right? And so you got one line, right? Here's line one. What are the three possibilities with respect to the other line? The other line could just be what? Any old which way. It could have a different slope than line one, like this, right?
It could be parallel.
It could be parallel. And then the other case, which you guys sometimes forget about, they could be literally the same line. Right? So, what is a solution to a system of equations? It is a point x comma y where both equations are true, right? So with two equations and two unknowns, there are three possibilities. A unique solution, here there is no point of intersection, so no solution. And over here, infinitely many solutions. See, because every point on the line is a solution. That's what we have to look forward to with two equations and two unknowns. The question then is, how do you find this point of intersection, or how do you decide that you're in one of the other two cases, right? And that's what we're going to be talking about, like starting on Wednesday. And we'll also look at how to solve three equations and three unknowns. Interestingly, the story remains the same. There's either a unique solution, no solution, or infinitely many. That continues to be true as long as we're working over what's called characteristic zero. Characteristic other than zero is something that no person in their right mind would talk about in college algebra. So even for me, it's a no. See you guys.